Good day everyone. Welcome to this presentation. I am Captain Ron Irani. In this video, I will be explaining the solution to problems in exercise 5 based on chapter 5, Effect of Density on Draft and Displacement from Captain Subramaniam's textbook, Ship Stability 1. Before I start with the problems, I will take you through a few slides explaining the theory and the formula that will be used in solving these problems. We all know that density is equal to mass upon volume. Now, when a ship is floating in a water of certain relative density and that same ship goes to the water of another relative density, what will change? Its mass stays constant. Only thing that changes is the underwater volume. And because the underwater volume changes, the draft also changes. Thus, if it was possible to pick up a ship physically and from a water of one relative density and put it into the water of another relative density, it will displace the mass of equal weights. The weight of the water displaced will be the same, in other words. Thus, when a ship moves from the water of one relative density to the water of another relative density, without there being any change of mass, the underwater volume will change. And as the underwater volume changes, and because draft has a direct relationship with the underwater volume, the ship's draft also changes. Going on to the next slide. Displacement in salt water is equal to the displacement in fresh water, and it is equal to the displacement in dock water. Now this is for the effect on box-shaped vessels only. Mass of the water displaced in salt water equal to the mass of the water displaced in any dock water. The mass is equal to underwater volume into relative density of salt water, and that is equal to underwater volume into the relative density of dock water. Thus we have underwater volume in salt water divided by underwater volume in dock water equal to relative density of dock water divided by relative density of salt water. So from this formula we see that the relative density is inversely proportional to the underwater volume. But we know that the underwater volume is equal to length into breadth into the draft. Therefore, when we substitute that in place of underwater volume, we have length into breadth into draft in salt water divided by length into breadth into the draft in dock water. And that is equal to relative density of dock water divided by relative density of salt water. The length into breadth in the numerator and denominator on the left hand side cancels out, and therefore we see that the relative density is inversely proportional to the draft. Now, given that the present drafts and density of dock water, we have to calculate the drafts in seawater, and this is what we are going to continue. The effect on box-shaped vessels only, please. We know that underwater volume is equal to length into breadth into draft. So when we substitute that, we find that, and we cancel out length into breadth in the numerator and denominator, we find draft in salt water divided by draft in dock water equal to underwater volume in salt water divided by underwater volume in dock water. Hence we see here that underwater volume is directly proportional to draft. With ships, these formulas should not be applied as the underwater volume is not of a cube for ships at any draft. Though the theory stays the same, the formula These formula that we have discussed above should not be applied. Instead, what is applied is something called as freshwater allowance and dock water allowance to get the new drafts. We know that TPC is equal to water plane area divided by 100 multiplied by the relative density of the water displaced. TPC in salt water therefore is equal to water plane area divided by 100 into relative density of salt water, which is 1.025. Likewise, TPC in fresh water is equal to water plane area divided by 100 into relative density of fresh water, which is equal to 1. Now, for example, let us take the dock water relative density to be 1.017. Therefore, TPC in dock water of 1.017 is equal to water plane area divided by 100 into the relative density of the water in which it is floating, which is 1.017. Moving to the next slide now. Freshwater allowance. Freshwater allowance is the number of millimeters by which the mean draft changes when a ship passes from salt water to fresh water or vice versa when floating at the loaded draft. It is found by the formula in millimeters. Freshwater allowance is equal to displacement in metric tons divided by 4 times the TPC, or in centimeters, freshwater allowance is equal to displacement in metric tons divided by 40 times TPC. The distance by which the summer load line can be submerged, called the dock water allowance, is found in practice by simple proportion as follows. Dock water allowance is equal to freshwater allowance multiplied by, in the numerator, 1025 minus the density of dock water divided by 25, or it is equal to freshwater allowance into 1.025 multiplied by the relative density of dock water divided by 0.025. In other words, we can simply write the formula as dock water allowance is equal to freshwater allowance multiplied by the difference in two relative densities divided by 0.025. Thus, if the ship goes from a water of lesser relative density to a water of greater relative density, the resultant will be negative. The resulting answer will be negative because dock water 1 here will be less than dock water 2. Simply put, the dock water allowance therefore has to be subtracted from the draft at which the ship is floating to arrive at the desired draft. The ship will rise because the draft reduces. If the ship goes from water of greater density to water of lesser density, the result will be positive. Dock water 1 has higher density than dock water 2. Hence, this answer will be positive. In other words, dock water allowance has to be added to the draft at which the ship is floating to arrive at the desired draft. The ship will sink because the draft increases. So just to recap it all, freeboards are measured from the top of the deck line to the top of the respective load lines. Tropical summer and winter load lines are basis the ship is floating in salt water. Fresh and tropical fresh load lines are basis the ship is floating in fresh water. freshwater allowance is the height from the top of the summer load line to the top of the fresh load line. Similarly, it is freshwater allowance is from the top of the tropical load line to the top of the tropical fresh load line. 1 by 48 height between the summer and winter load lines. Summer and tropical load lines and tropical fresh and fresh load lines is from the tops of the respective load lines. 1 by 48 height between the lumber summer and the lumber tropical load lines, and between lumber tropical fresh and lumber fresh load lines is from the tops of the respective load lines. 1 by 36 height between the lumber summer and the lumber winter load lines is from the tops of the respective load lines. Metric drafts are always even numericals, never with odd numericals, and drafts are read off from the bottom. Exercise 5, Problem 1. A ship of 16,000 displacement and TPC 20 is floating in salt water at a draft of 8 meters. Find her draft in fresh water. So given this data, what we have to find is the freshwater allowance. And we know that freshwater allowance is equal to displacement in salt water divided by 4 times the TPC in salt water. Displacement given to us is 16,000 tons. TPC given to us is 20. Thus in the denominator we have 4 times 20, and that gives us equal to 200 millimeters. And when we convert it to meters, it is equal to 0.2 meters. Thus the draft will increase by 0.2 meters. Therefore the draft in fresh water will be 8 plus 0.2 equal to 8.2 meters. So here we have the drawing. You have the two load lines. The green load line is in summer, and the blue load line here is of your fresh. The distance between the tops of these two load lines is your freshwater allowance, which we have calculated to be 200 millimeters. Thus, when she goes from salt water to fresh water, her draft will increase by 0.2 meters. Problem 2 states, a ship goes from relative density 1.008 to salt water. Find the change in draft if her freshwater allowance is 180 millimeters, and state whether it would be a sinkage or rise. She is going from water of lesser relative density to water of greater relative density. In other words, the ship will rise because the draft will reduce. Now, given to us in the problem, freshwater allowance is 180 millimeters and relative density is 1.008 of dock water. Dock water allowance is equal to freshwater allowance multiplied by the difference of the two relative densities divided by 0.025. Freshwater allowance 180, relative density of dock water 1.025, relative density of salt water 1.025, and relative density of dock water 1.008. The difference of the two multiplied by 180 divided by 0.025 gives us a dock water allowance of 122 millimeters. The ship is now going from 1.008 water to 1.025 water. That means that the draft will reduce because the ship will rise. The lines that are drawn over here for fresh and summer are basis the top of those respective load lines. Coming on to problem number 3. A vessel goes from water of RD 1.010 to fresh water. That means she is going from water of higher relative density to water of lesser relative density. And when that happens, the ship will sink. The draft will increase. If her freshwater allowance is 160 millimeters, state whether she would sink or rise and by how much. The data given to us in the problem is this, and from that we have to find the change of draft, that is dock water allowance. That we know that the dock water allowance formula is freshwater allowance multiplied by the difference of the two relative densities divided by 0.025. When you substitute all the values, you get the change of draft equal to 64 millimeters. She is going from water of greater relative density to water of lesser relative density, and hence the draft will increase. Problem number 4. Freshwater allowance given is 175 millimeters and she goes from 1.006 to 1.018. Find the amount of sinkage or rise. In this problem, she is going from water of lesser relative density to water of greater relative density. So in this case, the ship will rise. In other words, the draft will reduce. So change of draft is equal to freshwater allowance multiplied by the difference of the two relative densities divided by 0.025. Freshwater allowance given is 175. The higher relative density is 1.018. The lower relative density is 1.006 and you have 0.025 equal to 84 millimeters. Thus, when she goes from 1.006 to 1.018, the draft will reduce by 84 millimeters as calculated above. Problem number 5. A ship's stability data book gives her load displacement to be 18,000 metric tons and TPC to be 25. If she is now floating in dock water of 1.018, by how much may her load line be immersed so that she will not be overloaded? Now, what is given to us in the problem is her load displacement to be 18,000 metric tons. When it is said like this, it means that she is at her summer draft. Her summer load line is at the water line. And the displacement at that point is equal to 18,000 metric tons in salt water. So, what is given to us in the problem is that she is floating in water of relative density 1.018 with the top of her summer load line at the water level. If you see the drawing at the top on the right hand side, you will see that the water line coincides with the top of the summer load line, and she is floating in water of relative density 1.018. Now, if this ship were to go from this dock water directly into the sea without any loading of cargo. What will happen to her waterline? In the dock water, she was floating with the water line at the top of the summer load line. And when she goes into the sea, where the relative density of the seawater is 1.025, she will automatically rise by an amount equal to the dock water allowance, which in effect means that you have underloaded the ship, because when she is in the sea, in salt water, RD 1.025, that is when the water line must be at the top of the summer load line. So in effect, what happens is, in this present condition, the ship will float at this water line when she comes out into the sea. That means you have underloaded her by so much quantity, by so much draft multiplied by TPC. To calculate that, we have to calculate her dock water allowance and apply that while she is floating in the port in dock water of 1.018. And when we apply that, we see that we can actually load her until this point, so that when she will go out into the sea and will be floating in salt water of RD 1.025, her waterline will automatically come and settle at the top of the summer load line, which is shown to you in the drawing at the bottom. You can actually load her till this red line, which will be above your summer load line by an amount equal to the dock water allowance. Let's see the solution now. Freshwater allowance is equal to displacement in salt water divided by 4 times the TPC in salt water. Thus 18,000 divided by 4 times 25 equal to 100. That gives us freshwater allowance equal to 180 millimeters. Dock water allowance, the formula is, as we know, freshwater allowance into the difference of the two relative densities divided by 0.025. Thus, dock water allowance, when we substitute the values, is equal to 180 multiplied by the difference of 1.025 and 1.018 divided by 0.025 equal to 50 millimeters. Thus, we can load her 50 millimeters above the summer load line when she is floating in dock water of 1.018. Problem number 6. A box ship vessel 20 by 4 by 2 meters has a mean draft of 1.05 meters in salt water. Calculate her draft in dock water of RD 1.012. This is the data given to us in the problem, and we know that displacement remains constant even with the change of density. Therefore, displacement in dock water will be equal to displacement in salt water. Formula for displacement is equal to length into breadth into draft of dock water multiplied by the relative density of dock water, and that will be equal to the displacement in salt water. And formula for displacement in salt water is equal to length into breadth into draft in salt water multiplied by relative density of salt water. So length into breadth on both sides cancel out, and we have draft of dock water multiplied by relative density of dock water equal to draft of salt water multiplied by the relative density of salt water. Therefore, draft in dock water is equal to, when we substitute the values, we have 1.05 multiplied by 1.025 divided by 1.012. thus giving us draft in dock water equal to 1.063 meters. Problem number 7. A box-shaped vessel 18 by 5 by 2 meters floats in dock water of 1.000, which in effect is saying that she is floating in fresh water at a draft of 1.4 meters. Calculate her percentage reserve buoyancy when she enters salt water. The information that we can get from the problem is this: length is 18 meters, breadth is 5 meters, height is 2 meters. Relative density in fresh water is 1, draft in fresh water is 1.4. And we know that displacement remains constant even with change of density. Therefore, displacement in fresh water equal to displacement in salt water. Displacement formula being length into breadth into draft in fresh water multiplied by relative density of fresh water equal to length into breadth into draft in salt water multiplied by relative density of salt water. When we put in all the values and we bring the draft in salt water to the left hand side, we get draft in salt water equal to 1.4 multiplied by relative density of fresh water, that is 1, divided by relative density of salt water 1.025 equal to 1.365 meters. Total volume of the ship is equal to length into breadth into height. That is 18 into 5 into 2, which is equal to 180 cubic meters. Underwater volume in salt water is length into breadth into the draft of salt water, which is equal to 18 into 5 into 1.365. Now this 1.365 we have calculated above over here, thus giving us underwater volume in salt water equal to 122.85 cubic meters. Therefore, reserve buoyancy is equal to above water volume, which is the difference of total volume minus the underwater volume. That is 180 minus 122.85, giving us 57.15 cubic meters. And when that is converted into percentage, relative buoyancy as a percentage is equal to above water volume divided by total volume multiplied by 100. We have calculated above water volume is equal to 57.15. Also calculated above, total volume is 180, and you multiply 57.15 divided by 100. With 100 we get equal to 31.8%. Problem number 8. The hydrostatic particulars of a ship indicate that her displacement in salt water at a draft of 5 meters is 3000 tons. Find her displacement when floating at 5 meter draft in water of relative density 1.018. We know the formula for displacement equal to length into breadth into draft in salt water multiplied by relative density of salt water. Therefore, draft in salt water is equal to displacement in salt water divided by length into breadth multiplied by 1.025. Displacement in dock water of 1.018 is equal to length into breadth into draft in dock water multiplied by relative density of dock water. Therefore, draft in dock water is equal to displacement in dock water divided by length into breadth multiplied by 1.018 being the relative density of the dock water. Now what is given to us in this problem is that the drafts remain constant. She is floating at a draft of 5 meters in salt water, and we have to find her displacement when floating at the same 5-meter draft in water of relative density 1.018. So given that the drafts are equal, thus we equate this with this, and we find displacement in salt water divided by length into breadth into 1.025 equal to displacement in dock water divided by length into breadth into 1.018. Length into breadth on both sides cancel out, thus giving us displacement in dock water equal to 3000 divided by 1.025 multiplied by 1.018, which is equal to 2979.5 metric tons. Moving on to problem 9 now. A vessel displaces 4,500 metric tons of fresh water at a certain draft. Find her displacement at the same draft in water of relative density 1.020. Once again, the drafts are equal. The draft in fresh water is equal to the draft in dock water. So we have draft in fresh water is equal to this, and the draft in dock water is equal to this. We equate the two drafts. Draft in fresh water equal to draft in the draft in dock water is equal to the draft in fresh water. Thus, we have displacement in dock water divided by relative density of dock water equal to displacement in fresh water divided by relative density of fresh water. When we substitute the values, the only unknown being displacement in dock water, we find that is equal to 4590 metric tons. Problem number 10. A ship 100 meters long, 20 meters wide, having block coefficient 0.8, floats in salt water at a mean draft of 8 meters. Calculate the displacement. Calculate the difference in displacement when floating at the same draft in fresh water. Once again, we see that the drafts are equal, but in this problem we have got an additional information, that being block coefficient of 0.8. Displacement in salt water is equal to underwater volume multiplied by block coefficient multiplied by relative density of salt water. Displacement in salt water is equal to, when we substitute the values, we find displacement in salt water is equal to 13,120 metric tons. Now she is floating at the same draft in fresh water. Therefore, displacement in fresh water is equal to length into breadth into draft, which is also 8 meters, multiplied by block coefficient 0.8 multiplied by the relative density of fresh water 1, thus giving us displacement in fresh water equal to 12,800 metric tons. What is required is the difference in displacement when floating at the same draft in fresh water. We have calculated the two displacements at the same draft, this one being in salt water and this one being in fresh water, and the difference between the two is equal to 320 metric tons.